Chapter 3, Exponential Fourier Series, Introduction. You've seen series several times in your mathematical education. You saw geometric series, power series, Taylor series. All these have the summation symbol, capital Greek letter sigma. And that means we're going to be adding a whole bunch of individual terms. These examples here are all infinite series, which means there's an infinite number of these terms. In Circuits 2, you worked with trigonometric Fourier series. Again, this is an infinite series. We have the summation, and there's an infinite number of terms. And the trigonometric, because we're adding up a whole bunch of cosines and sines, each with a particular frequency, and each with a given scaling constant. In this course, we're going to use exponential Fourier series. They're related to the trigonometric Fourier series. This exponent gives us several mathematical properties which are very useful for development of signal theory. Remember that j is square root of -1. Mathematicians use I, but as electrical engineers we use j because we use I for current. You should have come across Euler's theorem someplace in your previous education, which says if we have an exponential, e to the j and some value, that's going to be cosine of that value plus j times sine of that value. In this class, we're going to use two other forms of Euler's theorem much more frequently. This says that the cosine of x, with this x value, is a complex exponential e to the jx plus another complex exponential e to the -jx divided by 2. And sine is a complex exponential e to the jx subtract e to the -jx divided by 2j. Note the minus instead of the plus, and the j, which is absent for cosine. You will want these on your note sheet for this course. If we're going to use exponential Fourier series, there's some other things you need to know. It only applies if our signal x of t is periodic. That means that if we were to shift that signal by any amount t naught, we get the same signal we started with. I think most of you know what a periodic signal looks like, but remember this definition. T0 is the amount which we're shifting by to make our signal repeat. T0 is our fundamental period. F0 is our fundamental frequency, and this is a linear frequency. Omega 0 is also our fundamental frequency, and this is an angular frequency. In this chapter, we're going to work on how to find omega naught, t naught, and a sub k in this equation that would apply to any particular signal x of t we want to study. Then we're going to look at how to use exponential Fourier series in the analysis of signals and systems.